Well, welcome back to our course on discrete mathematics. We're making some good progress as we're going through the three parts of what is in chapter one. We've already had two lectures where we started to break it down into propositional logic, how we can convert things into English, from English into propositions, and then predicates where we can be putting things in it that help us to modify it and set things up where we can be doing things like we have in part three, looking at proofs. And by way of just getting to this third part, let me just focus on this one chart again. And so here we have the propositional logic, the language of propositions, the applications and logical equivalences. We got a chance to be going over that information. Then we looked at predicate logic, where we're also including the idea of qualifiers, how we can be qualifying things that we're looking at from this predicate point of view. And finally, we're going to get into what the topic of this particular lecture is looking at proofs. So we have a couple different things that we'll be focusing on here. And so this is going to look at this. So we're going to be doing a lot of proving. And so first of all, we want to be getting things set up to be able to have valid arguments and rules of inference. That'll be the first thing that we'll talk about. We'll talk about the different proof methods that we can use, and finally, the proof strategies that are out there. So let's begin by thinking about the rules of inference. So later in this chapter, we will study proofs. Proofs in mathematics are valid arguments that establish the truth of a mathematical statements. By an argument, we mean a sequence of statements that end with a conclusion. By valid, we mean that the conclusion or final statement of the argument must follow from the truth of the preceding statements or premises of the argument. That is, an argument is valid if and only if it is impossible for the premises to be true and the conclusion to be false. To deduce new statements from statements we already have, we use rules of inferences, which are templates for constructing valid arguments. Rules of inference are our basic tool for establishing the truth of statements. So before we study mathematical proofs, we will look at arguments that involve only compound propositions. We will define what it means for an argument involving compound propositions to be valid. Then we will introduce a collection of rules of inferences in propositional logic. These rules of inferences are among the most important ingredients in producing valid arguments. After we illustrate how rules of inferences are used to produce valid arguments, we will describe some common forms of incorrect reasoning called fallacies which lead to invalid arguments. Then, after studying the rules of inferences in propositional logic, we'll introduce rules of inferences for quantified statements. We will describe how these rules of inferences can be used to produce valid arguments. These rules of inferences for statements involving existential and universal quantifiers play an important role in proofs in computer science and mathematics, although they are often used without being explicitly mentioned. So those are some things for us to be considering about. So we'll come back to our Socrates example, as now we're going to be played out in this third part, using all three parts that we have for this chapter. We have two premises: all men are mortal, Socrates is mortal, and then we have a conclusion: Socrates is mortal. So how do we get to the conclusion from the premises? That's the thing that we want to be looking at. So now we get a chance to be seeing how this might look, how we would write this out. So we can express the premises that is above the line, these two, and the conclusion below the line in predicate logic as an argument like that. We will see shortly that this is a valid argument. So we could prove that it is valid. So valid arguments, we will show how to construct valid arguments in two stages. So that's how we want to be looking at that first for propositional logic and then for predicate logic. So the previous two sections. So the rules of inferences are the essential building blocks in the construction of valid arguments. So first, for propositional logic, we use inference rules. Then for predicate logic, we use inferences rules for propositional logic, plus additional inferences rules to handle variables and quantifiers, which is what we talked about in the second part. In terms of arguments in propositional logic, an argument is in propositional logic is a sequence of propositions. All but the final proposition are called premises. The last statement is the conclusion. The argument is valid if the premises imply the conclusion. An argument form is an argument that is valid no matter what propositions are substituted into the propositional variables. So if the premises are P1, P2, all the way Pn, the conclusion Q, then, as we've listed here, is a tautology. Inference rules are all simple argument forms that will be used to construct more complex argument forms. So let's talk about a couple different rules of inferences, and so we'll take them one at a time. So here's the first one, modus potens, and you can be thinking of that of affirming the antecedent. And so this is what it can look like. And so here's an example. Here's the corresponding tautology, but here's an example. Let P be, it is snowing. Let Q be, I will study discrete math. If it is snowing, then I will study discrete math. It is snowing, therefore I will just study discrete math. So that's the first one, modus potens. Then we have modus tollens, which is denying the consequent. And so now we can see that we put in this negation here. And so here's the corresponding tautology. So let P be, it is snowing. Let Q be, I will study discrete math. If it is snowing, then I will study discrete math. I will not study discrete math, therefore it is not snowing. So that's kind of how it would be working with this. We also have a hypothetical syllogism. And so this is a logical argument that applies deductive reasoning to arrive at a conclusion based on two premises. And this is what the tautology would look like. And as an example, let P be, it snows. Let Q be, I will study discrete math. Let R be, I will get an A. So if it snows, then I will study discrete math. If I study discrete math, I will get an A. Therefore, if it snows, I will get an A. So we can see that's the rationale for using that syllogism. You can have a disjunctive syllogism. And so here we can see the disjunctive that we put in here. So let P be, I will study discrete math. Q be, I will study English literature. I will study discrete math, or I will study English literature. And so or is the operative word here. In some of the following charts, I actually highlighted that in red to make a point. So I will not study discrete math, therefore I will study English literature. For addition, here we have the tautology that we would have here. Let Q be, I will study discrete math. Let P be, I will study discrete math. Let Q be, I will visit Las Vegas. And so I will study discrete math. Therefore, I will study discrete math, or I will visit Las Vegas. So thus we can see that's one way we can be looking at it for addition and simplification. Here is a look at what the tautology is. And like P be, I will study discrete math. Like Q be, I will study English literature. I will study discrete math and English literature. Therefore, I will study discrete math. For a conjunction, here is the tautology that would be part of that. So let P be, I will study discrete math. Let Q be, I will study English literature. I will study discrete math. I will study English literature. Therefore, I will study discrete math and I will study English literature. Then we have resolution. Resolution plays an important role in artificial intelligence, and it's also used in Prolog. Here is what the tautology would look like. So if I let P be, I will study discrete math, and R be, I will study literature, and Q be, I will study databases, I will not study discrete math, or I will study English literature. I will study discrete math, or I will study databases. Therefore, I will study databases, or I will study English literature. We can also get into this where we're using the rules of inferences to build valid arguments. Valid argument is a sequence of statements. Each statement is either a premise or follows from previous statements by rules of inferences. And the last statement is called the conclusion. And so thus a valid argument takes the following form. So here we have all these statements, and then we get to the bottom where we have therefore a conclusion. So here's an example, and I'm not going to go through these solutions, but just give you a sense to look over them. So from the simple proposition here, show that Q is a conclusion. And so thus we can see how we go about solving this and what are the steps that we use to do that. So that's good. First example. Here's another one. With these hypotheses, it is not sunny this afternoon and it is cold. It is colder than yesterday. We will go swimming only if it is sunny. If we do not go swimming, then we will take a canoe trip. If we take a canoe trip, then we will be home by sunset. Using the inference rules, construct a valid argument for the conclusion, we will be home by sunset. And so here is the solution. And we're going to continue here. We get to the final proof for the second chart. And so here we can just see some of the steps that we would take for constructing the solution and then validating that. What about handling quantified statements? Valid arguments for quantified statements are a sequence of statements. Each statement is either a premise or follows from previous statements by rules of inferences, which include rules of inferences for the propositional logic and rules of inferences for quantified statements. The rules of inference for quantified statements are introduced in the next handful of slides that we'll see here. So here we have a universal instantiation. And so for an example, our domain consists of all dogs and Fido is a dog. All dogs are cuddly, therefore Fido is cuddly. And so we can get a chance to be seeing how that would work. We have a universal generalization. This is used often implicitly in mathematical proofs, and so you may want to be thinking about that. There's the existential instantiation. So this is the general format of what it would look like. And it's an example. There is someone who got an A in the course. Let's call her A and say that A got an A. There's the existential generalization as we list here. And you can think of it as an example. Michelle got an A in the class, therefore someone got an A in the class. Then we have using rules of inferences. We can use the rules of inference, construct a valid argument to show that John Smith has two legs. And it is a consequence of the premise that every man has two legs and John Smith is a man. And so here we can see how we come up with a solution to show how that would work. Here's another example. We use the rules of inference to construct a valid argument showing that the conclusion someone who passed the first exam has not read the book, follows the premise a student in the class has not read the book, and everyone in the class passed the first exam. So here is what the solution would look like. You can pause the video and go over that in more detail. And here is how we look at how whether or not the argument is valid. And so we can take it one step at a time to work through that. Okay, now we have everything we can need for the Socrates example. And so we flushed this into full logic designation, and we can draw our conclusion and make sense of that. And we can actually prove it. And here are the steps that we can be showing that we have a valid argument for in support of our conclusion. We have the universal modus potens. The universal modus potens combines a universal instantiation and modus potens into one rule. And so this rule could be used in the Socrates example. So that's an example of a place where it could be utilized. So it's like we're looking at a toolbox and we're getting a chance one at a time to use these different techniques. And so let's go ahead and start to leverage that as we go next into the section that talks about an introduction to proofs. Here's what we're going to be covering. In this section, we introduce the notion of a proof and describe methods for constructing proofs. A proof is a valid argument that establishes the truth of a mathematical statement. A proof can use the hypothesis of the theorem if any axioms assumed to be true in previous proven theorems. Using these ingredients in the rules of inferences, the final step of the proof establishes the truth of the statement being proved. So in our discussion, we move from formal proofs of theorems toward more informal proofs. The argument we introduced in section 1.6 earlier to show that statements involving propositions and quantified statements are true were formal proofs where all steps were supplied and the rules for each step in the argument were given. However, formal proofs of useful theorems can be extremely long and hard to follow. In practice, the proofs of theorems designed for human consumption are almost always informal proofs where more than one rule of inference can be used in each steps, where steps may be skipped, where the axioms being assumed and the rules of inferences used are not explicitly stated. Informal proofs can often explain to humans why theorems are true, while computers are perfectly happy producing formal proofs using automated reasoning systems. The methods of proof discussed in this chapter are important not only because they are used to prove mathematical theorems, but also for many applications in computer science. These applications include verifying that computer programs are correct, establishing that operating systems are secure, making inferences in artificial intelligence, showing that system specifications are consistent, and so on. Consequently, understanding the techniques used in proofs is essential both in mathematics and computer science. So, rough introduction to what we're going to talk about. We can think of proofs of mathematical statements. A proof is a valid argument that establishes the truth of a statement. In math, computer science, and other disciplines, informal proofs, which are generally shorter, are generally used. More than one rule of inferences are often used in the steps. Steps can be skipped. The rules of inferences used are not explicitly stated. It's easier to understand and to explain to people, but it is also easier to introduce errors. Proofs have many practical applications. Verifying computer programs are correct, establishing the operating systems are secure, enabling programs to make inferences in artificial intelligence, and showing that system specifications are correct. Well, let's talk about a couple definitions. A theorem is a statement that can shown to be true using definitions, other theorems, axioms, and rules of inferences. A lemma is a helping theorem or a result which is needed to prove a theorem. A corollary is a result which follows directly from a theorem. Less important theorems are sometimes called propositions. And finally, a conjecture is a statement that is being proposed to be true. Once a proof of a conjecture is found, it becomes a theorem and may turn out to be false if they can't find some way of validating it. For forms of theorems, many theorems assert that a property holds for all elements in a domain, such as the integers, the real numbers, or some of the discrete structures that we will study in this class. Often the universal quantifier is omitted by standard mathematical convention. So for example, the statement if x is greater than y, where x and y are positive real integers, and x squared is greater than y squared, really means for all positive real numbers, x and y, if x is greater than 0, then x squared is greater than y squared. Well, let's talk about proving theorems. For theorems that have this kind of a form, to where S is the arbitrary element of the domain, by universal generalization, the truth of the original formula follows. So we must prove something of the form if P then Q. So moving on, a trivial proof, if we know Q is true, then if P then Q is true as well. If it is raining, then 1 equals 1. A vacuous proof, if we know P is false, then P then Q is true as well. If I am both rich and poor, then 2 plus 2 equals 5. Even though these examples seem silly, both trivial and vacuous proofs are often used in mathematical induction, and we'll get into that in chapter 5. Okay, odd, even, and odd integers. The integers n is even if there exists an integer k such that n equals 2k, and n is odd if there exists an integer k such that n equals 2k plus 1. Note that every integer is either even or odd, and no integer is both even and odd. We will need this basic fact about the integers in some of the example proofs to follow, and we'll learn more about integers in chapter 4. So what about proving the conditional statement if P then Q? We can be thinking of the direct proof. Assume that P is true, use rules of inferences, axioms, logical equivalences to show that Q must also be true. In terms of an example, give a direct proof of the theorem if n is an odd integer, then n squared is odd. And so here is, you can walk through that solution and see what you think about that. Here's another one. The real number r is rational if there exist integers q, p, and q, where q is unequal to 0, such that r is equal to p divided by q. So we can look at, let's prove the sum of two rational numbers is rational. And so here we can see us walking through the details of how we could go about coming up with a proof for that. Here's another one, the proof of contraposition. Assume not Q and show not P is true also. This is sometimes called an indirect proof method. If we give a direct proof of not Q then not P, then we have a proof of P then Q. So I'm not going to answer this question, why does it work, directly, but you can be reading this example here and see what you think. Another example, prove that for an integer n, if n squared is odd, then n is even. And so how would we go about the approach? So we would use a proof by contraposition, assume n is even, that is not odd, therefore there exists an integer k such that n equals 2k. And so we can see the rest of it that we laid out here. We have shown that if n is an even integer, then n squared is integer. Therefore, by contraposition, if an integer n, if n squared is odd, then n is odd. So we can also look at proof by contradiction, also known as reductio ad absurdum. To prove P, assume not P and derive a contradiction such that P, that this proposition here, an indirect form of proof, since we have shown that not P, then F is true, it follows that the contrapositive T, then P also holds. So we're just starting to get a chance to get familiar with some of the proving methods and some of the tools that we've used for each of those. Here's a preview for chapter 4. Use a proof by contradiction to give a proof that the square root of 2 is irrational. And so here is the solution for what that would look like. You can go ahead and pause the video and look that over at your leisure. Here's another one, prove that there is no largest prime number. And so we assume that there is a largest prime number, call it Pn, hence we can list all the primes 2, 3, ... all the way up to Pn, and form this kind of a relationship. No, none of the prime numbers on the list divides R, therefore by theorem in chapter 4, either R is a prime or there is a smaller prime that divides R. This contradicts the assumption that there is a larger prime, therefore there is no largest prime. We can also have theorems that are biconditional statements. So to prove a theorem that it is a biconditional statement, that is a statement of the form that we show here, we show that if P then Q and if Q then P are both true. So an example that we can be using is prove the theorem if n is an integer, then n is odd, if and only if n is odd, n squared is odd. And you can look at that solution there and think about it more. So what is wrong with this? I'm not going to go through this in detail, but I quote proof that 1 equals 2. These are the kind of things that we can be doing in terms of manipulation. But is that something that we can actually hang our head on and say, yes, that makes sense? So looking ahead, if direct methods of proof do not work, we may need a clever use of proof by contraposition. So this is where it starts to get into the art form, where we are trying to figure out ways to do proofs, and we want to be using in an elegant way all the tools we have available. So we can be using contraposition, we can use proof by contradiction. In the next section, we will see strategies that can be used when straightforward approaches do not work. In chapter 5, we will see mathematical induction and related techniques. And in chapter 6, we will see combinatorial proofs. So there's a lot of tools in our toolbox, and we're just starting to get started with the things that we're covering in this chapter. Okay, what about proof methods and strategies? So we'll look at proof by case, existence proofs, disproof by counterexample, non-existent proofs, uniqueness proofs, proof strategies, proving universally quantified assertions, and then some open problems. So we introduce many methods that produce and illustrate how each method can be used. In this section, we continue this effort. We will introduce several other commonly used proof, including the method of proving the theorem by considering different cases separately. We will also discuss proofs where we prove the existence of objects with desired properties. So we briefly earlier we briefly discussed the strategy of behind constructing proofs. This strategy included selecting a proof method and then successfully constructing an argument step by step based on this method. In this section, after we have developed a versatile arsenal of proof methods, we will study some aspects of the art and science of proofs. We will provide advice on how to find proofs of a theorem. We will describe some tricks of the trade, including how proofs can be found by working backwards and by adapting existing proofs. When mathematicians work, they formulate conjectures and attempt to prove or disprove them. We will briefly describe this process here by proving results about tilling checkboards with dominoes and other types of pieces. Looking at tilling of this kind, we will be able to quickly formulate conjectures and prove theorems without first developing a theory. So we'll be walking through an example as we get a chance to push on with the material in this chapter. So let's think about proof by cases. So to prove a conditional statement of this form, we use the tautologies as listed here. Each of the implications P, I, then Q is a case. And so we're going to be handling a case at a time. So I'm not going to go through this in detail, but here is an example that you can trace through and see how you can be using proof by case. So we have case one here. And so we walk through that. A complete proof requires that the equality be shown to hold for all 6 cases, but the proof of the remaining cases are similar. And so we can go in and try them. So that's something that we can do, but we're not going to focus on that for this lecture. What about without loss of generality? We can, for example, we can show that if x and y are integers and both x times y and x plus y are even, then both x and y are even. And here's a proof to for us to be thinking about that. We could use the acronym WLOG for without loss of generality to have us think about that. I don't know if you've ever seen the movie The Man Who Knew Infinity, but it's about these two gentlemen, Godfrey Hardy and Ramanujan. Ramanujan wrote to Godfrey Hardy. Ramanujan was in India, and Godfrey Hardy invited him to come for an all expense paid to just be studying with him. A wonderful experience and some interesting things that they developed in terms of mathematics. And so here we can be looking at existence proofs and in a proof of a theorem of the form something like this. And so for a constructive existence proof, find an explicit value of C for which P of C is true. Then we can be analyzing this and see if it is true by the existence generalization or by an acronym e.g. One of the things that they played out in this movie that they were showing a taxi that had a number of 1729 and show that there is a positive integer that can be written as a sum of cubes of positive integers in 2 different ways. And these are the 2 ways that they could be looking at it. 10 to the 3 plus 9 to the 3. That would be one way of coming up with the number 1729. Or another one is 12 to the 3 and 1 to the 3. So some interesting, this is a proof of the existence that something like that does actually exist. We can have non-constructive existence proofs. In a non-constructive existence proof, we assume no C exists, which makes P of C true, and derive a contradiction. So if we prove that there's a contradiction, therefore, that's going to be a problem. Counterexamples, we mentioned that already. And so we can be thinking about this a little bit further. And here is an example. Every positive integer is a sum of the square of 3 integers. The integer 7 is a counterexample, so the claim is false. For uniqueness proofs, some theorems assert the existence of a unique element with a particular property, like this, that the 2 parts of the uniqueness proof are existence. We show that an element X with the property exists. And then uniqueness, we show that if Y is not equal to X, then Y does not have the property. And so an example that we can look at is show that if A and B are real numbers and A is unequal to 0, then there is a unique real number R such that A times R plus B is equal to 0. What about strategies for proving if P then Q? We can start by choosing a method. First, try a direct proof method of proof. If this does not work, try an indirect method, that is, try to prove the counter positive. For whichever method you are trying to choose a strategy. So now we're trying to think of strategic perspective. First, try forward reasoning. Start with the axiom and known theorems and construct a sequence of steps that will end in the conclusion. And if that doesn't work, try backward reasoning, where we try to prove Q, find a statement P that we can prove with a property if P then Q. We can be thinking about backward reasoning. And so here's an example. Suppose that two people play a game, taking turns removing 1, 2, or 3 stones at a time for a pile that begins with 15 stones. The person who removes the last stone wins the game. Show that the first player can win the game no matter what the second player does. And so I'm not going to go through this, but you can pause the video and go through these steps. And so this would be one of the ways that we can be using this strategy here, backward reasoning, to come up with a way of assessing that. In terms of universally quantified assertions, to prove the theorem of this form, we assume X is an arbitrary member of the domain and show that P of X must be treated using a UG. It follows, and I'm sorry that this is covered up. I'm just going to press on with the lecture. And so an example is an integer X is even if and only if X squared is even. And here is the solution that straddles over a couple of pages. We have cases. Here's case 1. We show that if X is even, then X squared is even using a direct proof. Case 2, we show that X squared is even, then X must be even. We use a proof of contraposition. And so we lay that out with contraposition looking at that case. Okay, here is, we're thinking about tiling and proof and disproof. And so what we're going to ask is, can we tile a standard checkerboard using dominoes? And the answer is yes. One example provides a constructive existence proof, and that's all we need to do is come up with an existence proof. And so you can look through the textbook to get a little bit more sense of that. Can we tile a checkerboard obtained by removing one of the 4 corner squares of a standard checkerboard? So basically, we see that the number 63 is not even. Our checkerboard has 64 minus 1, 63 squared. So this is not even, so we have a contradiction. So that's not going to work. Can we tile a board obtained by removing both the upper left and the lower right squares of a standard checkerboard? So it's a non-standard checkerboard. And so there are 62 squares in the board. To tile it, we need 31 dominoes. Key fact, each domino covers 1 black and 1 white square. Therefore, the tiling covers 31 black and 31 white squares. Our board either has 30 black squares and 32 white squares, or 32 black and 30 white squares. That's a contradiction, so it's not going to work. So what about the role of open problems? Unsolved problems have motivated much work in mathematics. Fermat's last theorem was conjectured more than 300 years ago. It has only recently been finally solved. And so here is the Fermat's last theorem. The equation x sub n plus y sub n equals z sub n has no solution in integers x, y, and z, with x, y, and z unequal to 0, where n is an integer with n is greater than 2. And a proof was found by Andrew Wiles in 1990, 300 years later. So someone was definitely thinking outside the box and figured it out. There's something called the 3x plus 1 conjecture. Let t be the transformation that sends an even integer x to x squared, x over 2, and an odd integer x to x3 plus 1 for all positive integers, where we repeatedly apply the transformation t until we eventually reach the integer 1. So here's just a couple example, and the conjecture has been verified using computers up to this value. So it's been verified, but that doesn't mean that it's been proved up to this point. So this is our last chart. There's also additional proof methods. Later, we will see many other proof methods: mathematical induction, structural induction, Cantor diagonalization, and combinatorial proofs. So mathematical induction, in which is a useful method for proving statements of the form that's shown here, where the domain consists of all positive integers. Structural induction, which can be used to prove such results about recursively defined sets. Cantor diagonalization is used to prove results about the size of infinite sets. And combinatorial proofs are used in counting arguments. All right, well, thank you very much for joining me in this lecture.